Hello, everyone. Thanks. So my name is Maxime Rossi Bellom. I'm a security research engineer and a team leader at Quarks Lab, and together with Damiano Melotti, also security research engineer at Quarks Lab, we are going to talk about the Titan M chip, and more precisely on how we perform vulnerability research on such a modern security chip. But before we start, let's ask ourselves, what is Titan M? So it is a security chip designed by Google for their Pixel devices, so for their Android smartphones. And on this component relies some of the most critical security features of the device, naming Keymaster Strongbox, Wither, AVB, and so on. So I will go a bit later in the next slides over these features. And it is important to keep in mind that this chip is, there is the main CPU on which you have Android and its application that are running. And you have another completely different hardware component, the Titan M chip. And these two will communicate together as a client-server model where the Titan M is a server and the main CPU a client. So Google introduced, at least according to them, they introduced this security chip in their devices in order to mitigate a wide range of side-channel attacks that were affecting the ARM trust zone. Because before introducing security chips in the devices, the security features I mentioned were implemented in the ARM trust zone. So just by having a completely separated chip that will execute these applications, it will mitigate these vulnerabilities. Also, there are a lot of hardware protections that are implemented in this chip, protecting against hardware reverse engineering and fault injections. So, at least on the paper, this chip is quite strong, quite robust against hardware tampering. Now, this is not the first time we speak about the Titan M chip. In fact, last year at Black Hat Europe, we presented our previous research on that chip, and we can summarize it as the following. So, first of all, we did reverse the firmware of the chip. We were able to find, it was not very difficult, but we were able to get the firmware file and to understand its format. It was not encrypted nor obfuscated, so it was not that hard to get into it. Yet there were missing parts of the firmware, at least on the files that we were able to look into, and there were some parts that were a bit more difficult to understand, like some state machines in the firmware. So this is why we wanted to find a way to interact with the chip. And in particular, we wanted to be able to sniff all the messages exchanged between the applications on Android and the chip, but also to send custom messages. So in order to do this, we started by implementing tools running in Android in a rooted device, and using a FreeDA script, we were able to sniff all the messages sent by the Android applications. And we implemented a tool we called Nose Client, and that we use that tool to send custom commands to the chip. And what is probably the most impressive, at least visually, work that we presented last time is what our colleagues, Philippe Tewen, thanks to his magic hands, did. He soldered each of every 64 pins of the footprint of the chip, that is less than 4 millimeters by 4 millimeters. And basically to perform a kind of man-in-the-middle attack on the chip. So we were, thanks to this setup, we were able to sniff all the communications going on, send custom messages, and all that from at the hardware level. The next thing we did was to find vulnerabilities, and we discovered two vulnerabilities doing static reverse analysis mostly. The first one allowed us to leak some parts of the boot ROM. So the boot ROM is the first piece of software that is executed in the chip, and we were interested into the boot ROM because reversing the firmware, we saw that there were some function calls pointing to the region where the boot ROM is. But using this vulnerability, we were only able to leak some parts of it, so we had to find another way to leak the full boot ROM. The second vulnerability is a downgrade issue that allowed us to flash any old firmware on the chip with the side effect that all the secrets will be erased. So we used this downgrade issue in order to flash an old firmware containing a one-day vulnerability that we previously identified. And by exploiting this vulnerability, we were able to leak pretty much everything that is present in the memory of the firmware, except the old secrets that were erased. So thanks to this, we have been able to leak the boot ROM, for example. Now, what did we learn about the chip? What do we know now? First of all, it is based on the ARM Cortex-M3 architecture, and this is quite common for microcontrollers. And the firmware is closed source, but it is based on an open source OS called EC for Embedded Controller that is designed by Google, written in C, and that targets the various microcontrollers of the Chrome OS project. This is why it is quite simple by design and quite small. For example, there is pretty much no dynamic allocations, meaning that all the things in memory are statically allocated. And most of the code is executed into tasks that could be compared to applications in bigger OSs. And regarding the buses, the two that are important for us right now or the SPI bus that is used to communicate with Android, and the UART that is not available by default unless you look a bit hard for it. And the UART is used for the logs and a minimalistic console. Now, what you see on the screen is a list of the tasks that we extracted from the firmware. The first two are used by the system to implement some features like events, timers, and so on. Then you will have one task per functionality. The first one, NuGet, is used to configure the system. It is the task you use to update the firmware. Then you have AVB for Android verified boots, and this task is involved in the secure boot of the main CPU. You have two of the tasks, face auth for biometric data, identity for identity documents, but we don't really care about those today. Then you have keymaster, that is, at least for today, one of the most important one. And keymaster is the backend of the key store, and whenever it relies on a security chip, like now it's the case for us, it is called Strongbox. And it allows applications to generate keys and use them directly from a safe environment, meaning the Titan M chip. The next task is Wither. It is used to store secret tokens. That's all. Basically, this task is used for the unlock feature, the screen unlock feature. And finally, there is the console task for where you will find some logs and the minimalistic console. Now let's have a look to how the communication with the chip is handled in Android. So the chip uses SPI to communicate with the main CPU, and then you have a kernel driver that will handle the SPI communications, and it exposes an IOCTL interface to userland daemons. And in Android, there is only one daemon that will communicate with the driver. It is the citadel-D daemon. And the goal of this daemon is to dispatch the various messages coming from HAL services. HAL is for a hardware abstraction layer. And these services, there is one per feature, one for Wither, one for Keymaster. And it translates the Android API that applications are using into messages generated with protobuf. So protobuf is this famous serialization framework made by Google. And in this case, what is very cool for us is that these protobuf definitions are present in IOSP's repository, meaning we can access them. And this is very convenient for the different various tools we are implementing, from the parser to the fuzzer. Now let's have a quick look to the firmware security. So as I said, there is no dynamic allocation, so it is not really a security feature, but it removes completely one class of bugs, so no use after free and similar things. There is a secure boot, as we could expect for a security chip. And then there is an MPU for memory protection unit. So it is like a simplified version of an MMU for memory management unit, except that it uses physical addresses. So there is no virtual memory, and so no randomized addresses. And it allows to define permissions like read, write, execute to memory partitions. And this particular MMU uses a custom interface to set the execution permission. And so by default, there is no partitions that are writable and executable, and this will become important later. The only software protections that we identified is then hard-coded canary, stack canary. But now we know that this feature were not there to protect against exploitation of buffer overflows, but rather to detect when an application is going crazy and allocating many things on the stacks. So today, we are going to speak about fuzzing, and we will show you how useful it is against the Titan, even though this chip is, this target is quite a constrained one. The firmware is closed source. There are a lot of interactions with the hardware, and the hardware is also quite a mystery. We don't have documentations or data sheets, so there are a lot of things to guess. We will cover two approaches. The first one is black box fuzzing. In this case, we don't have any ideas of what's going on in the chip memory. So we have to find heuristics to tell whether what we are sending to the chip is making it crash or not. And then we will cover emulation-based fuzzing. And in this case, we have a lot more insight of what's going on. We can have coverage or things like this, even though there are some limitations, and we will show you how we tweak them. Then we will speak about, we'll present how we exploited the vulnerability without debuggers or stack traces, and how using this single software vulnerability we were able to execute code on the chip and to compromise one of the most important security properties behind that chip. So now I'm going to let Damiano continue with the black box fuzzing.
Yes, here we go. So, fuzzing. We start thinking about automating vulnerability research, and the first thing that you can start to do is do it in a black box fashion. So, what we mean by black box fuzzing is essentially you throw stuff at your target. You only need a channel to communicate with it and a way to tell if it crashed. And based on that, we built on top of NOS client, so on top of this custom client that helps sending messages to the chip, we basically used this client to send random messages and then check what the return code we get back from it, what the return code is telling us. So if the return code is greater than 1, we can tell that something happened. And we can tell it because of as you can see in this header file, you have a series of return codes that can be given by the Titan, and the second one is particularly the one that corresponds to 2, so the third one, if you start counting from 0, is an interesting one. As you can see, application being stupid. This is the one that suggests that there was a crash, but also others like timeout or IO error can be interesting, are, let's say, faulty states that we are interested in. So we throw messages, we check the code. If it's greater than 1, we check what happened. So to put this into practice, we plugged libprotobuf mutator into our custom client. Libprotobuf mutator is a project also developed and maintained by Google. It is quite simple to use. All goes around the method that is called mutate, not surprisingly. And this method will apply some operators to the message you pass to add new fields or change their values. You, of course, trying to aim for known patterns for vulnerabilities. We start from a corpus made by empty messages, so that is not particularly complex because messages are not particularly complex, so after a few mutations they already become interesting. We just initialize some fields that are non-trivial, so we generate the right data structures to put there, and then we let the mutator do its job. And what happens, well, we did our first fuzzing campaign on a rather old firmware. It was the last one of 2020. And we found quite a few bugs, like, as you can see in the slides, buffer overflows, no point in the references, things that should not be there. One of the bugs, one of the buffer overflows, was the one that we exploited in the one-day vulnerability that gave us a code execution. This was, as I said, an old firmware. So then we saw it was working. We saw we could get good results. So we tried to do it again with the latest firmware. And we found out that 2 of the null pointer, the references, were still there. Actually, it's 2 commands that triggered the same function that has the bug. We reported it. The bug was making the chip crash, and you had to reboot the chip or the phone. That implies rebooting the chip to make it work again. But Google did not consider it serious enough to be a vulnerability and end up in the bulletin. All these results came after just a few minutes of fuzzing, and that brings us to the comments and limitations of the approach. Because first of all, if you get bugs, in the end, that's what you're looking for. So that's a good point about this approach. We get bugs. It's very simple to get bugs because, as you have seen, we haven't done anything special. Just plugged the mutator and did a bit of mutations on the messages. The performance is also decent. Now, if you're used to fuzz native binaries, this will look like a ridiculous number, but it's not that bad for a chip like Titan M. And most importantly, we are testing in the real device. So if something happens, you probably already have your proof of concept ready. At the same time, we are probably only exercising shallow states with black box fuzzing. We don't know what's going on the target. It's very likely that we stop very early in the processing. So this is a negative aspect. Our approach is also potentially prone to false positives because, as we have seen, we check for the return error, but that doesn't necessarily mean there was a bug when an error was not the one we expect. And detecting on the same line is kind of tricky because unless something happens, you don't know if there was a corruption or anything. And then there is one last point that we want to point out, that when you throw these many messages, there is a risk that you may break something. So just keep this into account if you will ever apply it. Things can break, and it happened once for us. So just to keep into account. But really, the bottom line is that it's good that you test on the real target, but you don't really know what is going on. So that's when we started to think about emulation-based fuzzing, which completely changes the approach. Because instead of testing on the real device, we take the firmware and we run it ourselves. And we can do it because after hours and hours of reverse engineering, now we have an idea of how it works. We also can help ourselves by leaking arbitrary memory thanks to the old vulnerability that we exploited. So if we don't know how the memory looks like, because it's not statically defined, we can help ourselves with that. And with emulation, we are in control. We know which instructions we hit, and we can take a much closer look to what's going on. And that is the perfect feedback, or at least a very good one for a fuzzer. So when it comes to emulating Titan M, of course, there are several frameworks out there. We played with a few of them. And in the end, we ended up using Unicorn, which is built on top of QEMU. And this was a convenient choice for us because it only emulates the CPU. So it doesn't try to be particularly smart. You just emulate the CPU, but that's what we want because we also have a custom OS, so we don't really know how to set it up in a full fashion. It is really easy to start emulating with Unicorn, and it integrates very nicely with AFL++, which is going to be the next thing. So AFL++, I'm sure most of you know what it is. So it's little bit of the state of the art when it comes to fuzzing today. And it has a unicorn mode, which essentially allows to fuzz pretty much anything that you can emulate with unicorn. And then you get the classical AFL experience with the interface and everything, which is probably one of the main selling points of AFL. You only need to place your input somewhere, so there is a callback for that. Usually this is a static address where your input is always placed. And you get the crashes when unicorn crashes. So for example, when you try to read or write in a memory page that you haven't mapped. You can also plug different mutators depending on your needs with AFL++. And this was particularly useful for us, as we will see in the next slides. So now we don't have anymore to focus on the one thing, the one channel we have, like in black box fuzzing. When you are emulating, you can basically fuzz, as I said before, whatever you want. All you need is a value to put in PC to start from, and a good memory state with registers, with memory and registers. And then you need one or more points where you want your emulator to stop. But of course, remember to keep attack surface into account. Remember to fuzz something that is actually reachable then by untrusted input. So that's something to remember. And one interesting vector that we identified is the one of SPI rescue. This is a feature that allows to recover the firmware of the chip. Can be triggered without needing the user password, but it will wipe all the data that were stored inside the chip. The firmware is sent in a particular format that you see here on the slide. It has some hashes before and after the actual code. So we took this feature and we thought, what can we do with it? Is it something we can explore? And since with SPI rescue we can flash new images, now most images will not actually be able to run because there is a secure boot, but we can flash them. So an interesting vector to test is the loader of new images. So, and this happens in the boot ROM. So this is placed in the boot ROM. So since we managed to leak it with the old vulnerability, we wanted to take a closer look to it. And of course, a bug in the boot ROM is more serious than another one because it's way more tricky to mitigate or to patch. But at the same time, the boot ROM is simple, has to be simple. It's only 16 kilobytes. So the only thing essentially we could try to test was the image loader. So assuming we could flash stuff with SPI rescue, see if we could find anything. But no, we couldn't. So the function is really simple. It only essentially takes the header file and launches the next stage, the next loader. And also the samples are just these header files. There isn't really much to mutate and to corrupt. So this was a first failed attempt. Still focusing on the SPI rescue, instead of fuzzing the loader of new images in the boot ROM, we fuzzed the handler of the feature that was responsible of receiving the files from the Android side and physically writing them on the flash. And this time, we wanted to see whether this processing was happening correctly. And the input this time is also a bit more structured. We have these rec packets. And to mutate them, we plugged a different mutator, which is actually a bigger project. It's called Format Fuzzer. And this is essentially a framework that allows to generate and mutate binary files based on a template that is the BT template of the 010 editor. And it runs on a modified version of AFL++. Unfortunately, also in this case, no serious vulnerabilities were found, but we did found some interesting stuff. For example, we understood that packets, the footer hashes were completely ignored by TitanM, or that these hashes had every 0 byte replaced with a 1 for some reason. So this is like stuff that I think I wouldn't have discovered with simple reverse engineering, because when you want to build a harness on top of an emulator, you really need to understand every single line of the code, and that's usually something that you don't do when you do static reversing, or maybe I'm just a bad reverser, that's it. So in the end, we decided to go back to the tasks, the same thing we did with the black box fuzzer. So we put again with our emulator libprotobuf mutator. This time we only needed to take care about a way of telling which message we were about to send, because you can only send a stream of bytes from the mutator to AFL. And we fuzzed mostly 3 tasks: identity, keymaster, and weaver. But especially identity and keymaster are the bigger ones, and those that have to do with more complex messages. So first of all, can we find the same bugs we already knew about? Because otherwise, we are not going the right way. And the answer is yes, all of them, apart from one. And that one, we will be discussing about it in a second. But just a few comments on emulation, because like we've been taught, there is no free lunch. Emulation is not a silver bullet, and in embedded targets like these ones, you will find plenty of hardware-dependent code, which simply cannot be emulated unless you want to emulate the peripheral behind it. So what we did was just ignoring it, hooking it, which reduces the amount of code that you can actually exercise. Also with emulation, there are limitations in the bugs you can detect because there is no ASAN other sanitizer like instrumentation. If you have an overflow within the same page or a one-off by one, these kind of things cannot be detected automatically by Unicorn. And then this is a consequence of our choice. We didn't want full system emulation. We didn't get full system emulation, so you are going to fuzz a specific part of the code, and the bug we missed it because it was in the scheduler of the tasks that we were not emulating, so good luck in finding that. That was part of the game. So a few tweaks that become possible when you have emulation really go in the direction of tweaking your logic to have more, monitor more things, more hooks. So we were monitoring consecutive reads in low addresses where the boot ROM is placed, because we identified there was a pattern there of vulnerabilities trying to copy code from the boot ROM. We also had some monitors inside, well, close to some global buffers that could be overflown, but at some point you have to trade off between how much you monitor, how much you hook stuff, and how much you let your fuzzer run, because reverse engineering takes time, and you cannot just do it for everything. And also take into account that the hooks will impact performance. So the more hooks you have, the slower the emulator will be. In our case, it wasn't a big deal though, because we were fuzzing really specific chunks of code. So, but I mean, we are here to present one of the vulnerabilities, a vulnerability that was found with emulation, and how we exploited it. So let's get into it. The vulnerability is in this function that is meant to essentially parse some fields inside the key, protobuf messages, key parameter fields, as you can see on the slides. And in particular, finding digest tags inside these key parameter messages. The vulnerability is an out-of-bounds write of 1 byte that can be set to one. So this can be repeated actually multiple times, but there are some constraints on the offset, as we will see. So like at first we thought, okay, this is a really minor issue, but let's dig into it. So this is the code, assembly code on one side and decompiled on the other for the bad reverse engineers like me. So this is the vulnerable instruction. So store byte R1 is 1, and it can be in an offset that is partially unchecked. And the checks that happen, let's start from a random 32-bit value. So we apply a mask, first of all. So we ignore 3 bytes out of 4. Those are going to be set as we want. But we concentrate on the last byte, and this last byte has to be smaller or equal than 4. Otherwise, we jump into that if, and we return. So the 5 most significant bits need to be 0, otherwise the value will be too big. And then we have this weird shift and AND operation here. Bear with me and just trust me that the last bit needs to be 0, because otherwise, again, we will hit the if condition. So the least significant byte of our offset needs to be 0, 2, or 4. So we only have 2 bits of freedom. So at this point, what can we do? There are different code paths that will lead to this function. And this means we can get there with different base addresses where we will have our out-of-bounds write. Then remember that the memory is completely static. Functions and the global structures and stuff will always be at the same address. There is no randomization or anything. So really, setting 1 byte can be enough. Can really be enough to do interesting things. You can think of many different options, such as just denial of service, or maybe setting that famous admin flag, or even edit a sides field and then cause another corruption. So there can be space to do stuff. So what we did was, let's generate all the addresses that we could be able to write based on the different code paths, highlight them in Guidra, and then start looking at them, see what we can do. And then at some point, we realized that we could write into this structure in memory. We called it keymaster SPI data. And we could overwrite 1 byte in that field, setting it to 1. That's the only thing we can do. So keymaster SPI data is a global structure that actually there is one for every task that communicates with Android. So you have identity SPI data, Weaver SPI data, and so on. It stores information about the SPI exchanges with Android. And in particular, the field we can overwrite, or at least where we can overwrite 1 byte, is the one where you store incoming requests. So now it was 192C8, and by overwriting it, it becomes 101C8. So now requests will be stored quite far from where they would be supposed to. And that's where we started to have fun. But remember, all we have is a client that sends custom messages, and we get back 1 return code, which perhaps tells us that there was a crash or something like that. No logs at all on logcat, or at least useless logs. And that's pretty much it. So if you want to write an exploit with these primitives, it can be a bit of an adventure. But we have been keeping something, and this is the UART of the chip. So there is actually a little story about this UART. Initially, the device I was testing on wasn't enabled with the UART. Then we did this work also on another device to start digging into this vulnerability. But basically, the Titan M chip exposes two pins on the board, as you can see from the picture. And you only need to solder 2 wires to have the UART of the chip. And here you also see the USB connector that we can plug into our laptop. This console is really, really simple. You can only essentially send messages about and get to know things about the state of the chip, the version, these kind of things. But although this doesn't provide any information on what goes wrong when something goes wrong, so forget about stack traces or stuff, this is still very useful because this is the place where Titan M prints its logs. So if when printf or log is used, the logs will end up here. So what is there in this new address that we are storing the requests in? Well, we will not explain the full memory layout of Titan M, but all you need to know is that their data doesn't really seem to be used. So what we tried to do is, okay, let's try to write their messages bigger and bigger and see what happens. In the meantime, we monitor what goes on in the UART so that if we see some crash, some log being printed, we know that something is happening. So that's what we do. We build bigger and bigger and bigger exploits. And then at some point, we realize that the chip starts crashing with a specific length of our payload. So here the UART comes very helpful, because what can we do? What happens if we put a function that is supposed to print some logs in the UART right there at the end of our payload, where we see we are making the chip crash? And the answer is we get the logs on the UART. So the logging function is executed. We have code execution. So at this point, what's going on? Our guess is that we are writing on the stack of one task that pushed a return address on the stack at some point, and we overwrite it, but then it gets executed. So from here on, things start to get really complex on the exploitation side, because we cannot write a ROP chain there exactly. We need to move the stack pointer, because otherwise the chip will crash. It gets complicated, but in short, we solved it by sending another command that would trigger another ROP chain that we would write elsewhere. We will be publishing one or more blog posts about it, but it's really about making sure that the chip doesn't crash and your ROP chain or your ROP chains will be executed correctly. But now I'll hand it over again to Max to go over the impact of this vulnerability. Does it work?
Doesn't work? Okay, thanks. So now let's have a look to the impact of this vulnerability. Not only the impact on the chip, the Titan chip, but the impact on the whole device security. So we control the execution flow of the chip, and something that would be great would be to write our own code, and for that we need a memory page that is writable and executable. There is no such pages. So what we could do is reconfigure the MPU. But because this MPU is using a custom mechanism to set the execution permission, we cannot do that. Yet there are a lot of things that we can do just by reusing the code of the firmware, so implementing route chains. And we implemented a leak command again in our nose client tool, but this time based on the zero-day Damiano just presented. And since we are not downgrading the system to exploit this vulnerability, there is no data loss, meaning that we can leak pretty much everything that is stored in the chip's memory. So if you look at this example, I'm not sure you can see it on the screen, but here we are calling the leak command. The arguments are first the address, it is 0, and then in hexa it's 16. So we are leaking the 16 bytes at the address 0, and at the address 0 there is the boot ROM. So what you can see are the first bytes of the boot ROM. Now, can we use this vulnerability and do something more harmful for the device security? For example, can we leak strongbox keys using this vulnerability? So first, a short reminder about strongbox. Strongbox is the hardware-backed version of the key store, and the task that handles this feature in the Titan is called keymaster, and it allows applications to generate and use secrets directly from the chip, from the Titan memory. But what is important to keep in mind is that the Titan does not store the keys, and instead they are placed in an object called a key blob. And this key blob is encrypted by the Titan with a key called key encryption key. And this key is derived from several internal elements inside the chip, so we will come to that in the next slide. And whenever an application wants to use a key blob, a key, it will send. Not directly, in fact, there are daemons in Android that will do that for the application. So the system will send the key blob to the chip will decrypt the key blob, perform the operation, and send back the result. And a side note is that the root user on Android can use any keys. And that's quite interesting. There is no way for the Titan to tell if a key is owned by an application or another. So for the Titan it receives keys and it uses them. However, root user or any other user should never be able to extract a key from the memory of the chip. Now let's come back to these key encryption keys. They are derived from 3 components by a mechanism called the key ladder. And this key ladder is still quite mysterious for us since we did not reverse it fully, partly because it is implemented in hardware. Yet what we can tell you about it is that there are 3 main elements that are used to generate the keys. The two second ones are the root of trust that is sent by the bootloader of the chip and a salt that is randomly generated. So these 2 elements, we can leak them since they are stored in a persistent memory of the chip that is readable. However, there is also an internal root key that is not available from software. So we can leak 2 out of 3 elements, meaning we cannot replicate, we cannot regenerate the keys. So how can we leak strongbox keys using this vulnerability? Now, let's have a look to the commands that are used by the system to perform cryptographic operation using strongbox keys. So the first command is called begin operation. And it contains in inputs the key blob and some characteristics that describe the key and the operation to perform, like signed with an RSA key of size whatever. And the chip will receive this command, extract the key, and store it, save it for later into a fixed address. So from now, you should see where we are going. Then there is another command called update operation, and it contains the data on which the operation must be performed. The chip will encrypt, decrypt the data, or whatever, and return the output. So this command can be called several times depending on the size of the data. And finally, there is the finish operation that does pretty much the same as the update operation command, except that it will end the operation. So our strategy is simple. First, we get the key blob from the device, and the key blobs are stored in the Android file system, in a database in the key store directory. Then we forge a begin operation request using this key blob and some characteristics that we also can get from the database. We send this command to the chip receives it, it will decrypt the key blob, store it at a fixed address. Then we can use a vulnerability to leak the key, the decrypted key. So we implemented a command that we call leak KB for key blob in our nose client. And if you look at this example, the first command allows to list all the strongbox keys from the database. So here in our case, there is only one called strongbox. It's an AES key of 128 bits. Then the second command allows to leak the key from the chip memory using the strategy I just presented. So you can see in this example, we successfully leaked an IIS strongbox key. Now, there are some conditions that we would like to remind that there are some requirements in order to perform this attack against the device. And the first thing is that you need to be able to send commands to the chip. And to do that, in our case, we rooted the device, but it's in real life, you would need some vulnerabilities to elevate your privileges and in order to be able to discuss either with the driver or the Citadel daemon. Or you can do something like we presented at the beginning of this talk, meaning to access the SPI bus at the hardware level. A second requirement is to access the key blobs, and here again you need enough privileges to access the database. So being root is nice, but it requires some privilege escalation vulnerability before being able to do that. Or you can find a way to bypass the disk encryption, but it may be even harder. So just to this is just to show that this is not that easy to get to the point where we can leak the keys. So we want also to present this mitigation. So this is not a mitigation for the vulnerability on the Titan M, but it will make the leak of the strongbox keys more difficult since it had an extra layer of security. By using in the application, whenever the developer wants to generate a key and use it, it is possible to add to call the method set user authentication required. And whenever it is set to true, what happens in the background is that the key blob is encrypted a second time with a key derived from the user password. So it needs now, to leak a key, you now need to break 2 layers of encryptions. And by the way, using this option, the root user cannot neither use the key unless it has the password of the user. So that's it for this vulnerability and this talk. Now, a little conclusion. So we showed that fuzzing can help to find more bugs. And we presented you the black box approach. And even though there are limitations, we can get some interesting results. You can easily get some surface bugs. And while with emulation-based fuzzing, we have a better idea of what's going on, and it's quite efficient on such targets. Yet, we have to implement a few tweaks in order to optimize the results. So we discovered a very severe 0-day, and it allowed us to execute code on the chip and to leak pretty much everything from the chip's memory. And it also allowed us to break one of the most important security properties of the chip, meaning to leak strongbox keys. So thank you everyone for listening. By the way, the materials of this talk will be soon added into our GitHub repository. In the meanwhile, you already have the materials of the previous talks that are there. Thank you again, and if you have questions, feel free to ask.
All right, so are there any questions?
Hello, thank you for the nice presentation. On a rough estimate, it's hard for me to understand from the black box perspective, how long did it took you to go all the layers down even deeper until you were able to leak the strongbox key?
How long?
Yeah,
how long for starting from 0 to leaking the strongbox keys? Yeah.
In terms of time, you mean? Or in terms of what?
No, in terms of how long you took for the research in like person days, months.
Okay.
For the project, it's difficult to tell because it's not something we do full time. So it's a side project, even though we have dedicated time for that in the company. And also there are a lot of things that we did not present it, many dead ends. So yeah, it's very difficult to give an answer. We started more than a year ago, and we spent hundreds of days on that, definitely, on the whole thing, including making the slides and and things like this.
Yeah.
Okay. Thank you.
Any other questions?
Hi, great talk. Thank you for that. Are you going to look at other Strongbox implementations too? Any plans for that?
Are we going to have a look at other Strongbox implementations?
It is not planned. If you have suggestions.
No.
But yeah, so other vendors are building similar chips. So to have Strongbox, you need the separated hardware. Like TEE is another security level that is considered less secure. So I guess it will depend on how complex it is to start approaching another chip. I don't know about Samsung has one, for example, but some research was published also. So yeah, we might consider that in the future, but it depends on how other vendors are doing this stuff, basically.
All right, so if there's nothing else, this concludes this talk and also this track, so, because the last talk that was planned for this track is going to be moved to track 1. So if you're interested in that, please get to track 1. Thank you very much, everyone. Thank you much to you too, and let's thank the speakers again.